Hello students, under the chapter Rotational Dynamics, today we are going to discuss about the applications of uniform circular motion. Here we are going to consider the motion of a vehicle along a horizontal circular track. We know that while traveling, sometimes we have to take a turn. In this figure, the turn is towards left. The vehicle may take turn to the right also. Here you are marking that the center of the circle is on left hand side of the figure. Here is the vehicle. When you are drawing the vehicle, don't forget to draw the wheels to the vehicle. This is a curved road and R is the radius of curvature of this circular track or circular road. The road is such that its surface is horizontal. You know that on the turn, sometimes the road surface is not horizontal, that is the outer edge. This is the outer edge of the road, this is the inner edge of the road. This outer edge is raised with respect to inner edge. That road is known as bank road. This is a simple road, horizontal road. It is a turning, means circular track is there, but it is horizontal, there is no banking. In this case, we are going to find out what is the maximum speed with which this vehicle can be driven so that there is no danger to this vehicle. Now, we are going to find out the maximum speed. For that, we are going to see what are the different forces acting on the vehicle. Here we are considering the vehicle as a single point. This is the center of gravity of the vehicle and the different forces, that is weight of the vehicle is naturally mg and it always acts vertically downwards. This is mg, and the normal reaction, it acts normal to the surface and it is exactly in upward direction. And the third force is the frictional force. Force of static friction, Fs. As we know, this force provides the necessary centripetal force for the circular motion. And the centripetal force, as you know, is mv square by r. Here we are considering that the vehicle is moving with a constant speed along this curved road, and that speed is v. Now, we are balancing the different forces in order to have equilibrium. Therefore, in equilibrium condition, you are observing here that mg and n are in exactly opposite directions. Therefore, I will write here n is equal to mg. And as we have seen right now, the force of static friction Fs, it provides the necessary centripetal force for circular motion. Therefore, Fs is equal to, the centripetal force means mv square by r, where r is the radius of the curved road. Now, suppose this is equation number 1, this is marked as equation number 2. Then we divide the second equation by the first equation to get F by N is equal to mv square upon r divided by mg. So this m cancels with this m, giving us v square upon rg is equal to fs upon n. Now this is the limiting force of static friction. It has some maximum value. You know that if mu is the coefficient of static friction, then the maximum value of Fs is mu into N, or according to first law of static friction, the limiting force of static friction is directly proportional to the normal reaction. So when we write it in the form of equation, then we get Fs is equal to mu into N. Therefore, Fs divided by N is equal to mu. Therefore, we will substitute the value of Fs upon N as mu. Hence, we write here mu is equal to v square upon rg. We are going to find out the maximum speed. Therefore, I will transfer this rg to the other side to get v square is equal to mu rg. Hence, by taking square root of both sides, I will get v max is equal to under root mu rg. So this equation number 3 gives us the maximum speed with which the vehicle can be safely driven on the curved horizontal road like this. Now, this is a horizontal circular track. Means there is no banking. Here in the equation there is mu rg. So, mu is coefficient of static friction. And in the rainy season, mu decreases. Also, if there is some oil sprayed on the road surface, then also the value of mu decreases. Therefore, mu is not reliable. Hence, we bank the road. So, there is necessity of banking of the road in order to have safe driving. That we shall see later on. Now, let us talk about toppling. Suppose this is the surface and this box is kept in this manner on this surface. Then this condition is known as toppling, that is falling down. Suppose there are number of bicycles standing side by side in our college cycle stand. Suppose a bicycle is given push towards the other, then all the bicycles will fall down one by one. This is known as toppling. We have to find condition such that the four-wheeler should not topple. For that, again, we are going to consider here a four-wheeler which is taking a turn on a curved road towards left and the road surface is horizontal. Under this condition, we are going to find out what is the maximum safe speed so that this vehicle will not topple. For that, again, we will have to see various forces acting on this vehicle. As usual, it is the center of gravity of the vehicle. This center of gravity is at a distance small h from the ground level. Then there are two wheels of the vehicle are on the left hand side, that is inner side of the road, and two wheels are on the outer side of the road. Let R1 be the normal reaction on inner wheels and R2 be the normal reaction on the outer wheels. This is the center of gravity G of that car or four-wheeler, and as usual, the weight of the car or four-wheeler will act vertically downwards, and its magnitude is mg. The another force acting on this car is the force of static friction, which provides the necessary centripetal force for this circular motion. So, as it is centripetal, its direction is towards the center. So, this force F is acting towards the center of this circular path. In order that this vehicle should not topple, it is in equilibrium, we will have to balance the different forces in this case. As we are observing here, the normal reactions R1 and R2, they are in vertically upward direction, and mg is in downward direction. Therefore, we get the equation R1 plus R2 is equal to mg. Under equilibrium condition, these forces should be equal. The sum of R1 and R2 must be equal to mg. This is first equation. The second thing is that this force of friction, it provides the necessary centripetal force. Therefore, F is equal to mv square by r. V is the speed of the vehicle with which the vehicle is moving along the curved road. M is mass of this vehicle and R is the radius of curvature of the road. F is the force of static friction. So, this is equation number 2. Now, as there is no rotational motion produced in equilibrium, that is no toppling condition, moment of these various forces about any point must be equal to 0, or the clockwise torque must be equal to anti-clockwise torque. For that, let us see moment about this point G. For this point G, we will have to find out the torque or moment of the force due to R1. moment of force due to R2, moment of force due to F, moment of force mg. Initially, for obtaining this moment of R1, we must here denote this distance from center of gravity to R1 as A. Here also the distance of center of gravity from the outer wheel is A again. That is, distance between two wheels is twice A. Here, when I have to find out moment of this R1 about G, then I will draw a perpendicular from this point G like this. Now, if this is a rod and due to R1, it will turn like this about point G, means this is a clockwise torque, means R1 produces a clockwise torque. Perpendicular distance between this G and R1 is A. Hence, the moment of R1 about G is obtained as R1 into A. Now this another force is the frictional force. Again for that, what we shall do is, we will draw a perpendicular from G on this F, and here we are observing that this rod will move in this manner due to this force. That is, this direction is again a clockwise direction, and the distance between, the perpendicular distance between this point G and force F is H. Hence, as it is again clockwise, we write F into H and add it to R1A, which is in clockwise sense. There is no moment of this weight produced about point G because it acts at the same point. Its distance from point G is 0. About this R2, now again we will have to draw a perpendicular from point G on R2, and as seen here, this, due to this reaction R2, the rod will move in anti-clockwise sense. Therefore, it produces anti-clockwise torque, and this distance is again A. The distance of point G from R2 is again A. So, it is R2 into A. Therefore, the anti-clockwise torque is R2 into A. When the clockwise torque is equal to anti-clockwise torque, the vehicle will be in equilibrium. Now we transfer this term to the left hand side so as to get FH is equal to R2 minus R1 into A. We have this equation number 2. So from equation 2, we get mv square upon R into H is equal to R2 minus R1 into A. Let us transfer this A to left hand side. So we shall get mv square H upon RA is equal to R2 minus R1. From this equation number 3, it is clear that R2 is greater than R1. That is normal reaction on these outer wheels is greater than the inner wheels. As the velocity goes on increasing, the R2 goes on increasing, or R1 minus R2 goes on increasing. This equation shows that sum of R1 and R2 is mg. If R2 increases, R1 will decrease. When the velocity increases, naturally R1 minus R2 will increase. And here from this equation, if R2 increases, R1 decreases. So a situation will come when R1 becomes 0. Under that condition, what happens? This wheel, inner wheel, it loses contact with the road surface and it now begins to topple. It tends to topple rather. Now we are making this R1 0. And when R1 becomes 0, we get the equation as R2 is equal to, when R1 is equal to 0, then we get mv square h upon Ra is equal to R2. As R1 is 0, R2 is equal to mg. Using now equation number 1. When R1 is equal to 0. So R2 is equal to mg. R2 is equal to mg. Hence, putting the value, we get mv square into h upon Ra is equal to mg. Now, this m will cancel with this m and v square will be now equal to, v square is equal to Gra upon h. The maximum speed will be obtained by again taking square root of the above equation, that is v will be equal to under root Gra upon h. When the speed of the vehicle is less than the speed given by this equation 4, there is no danger of toppling of the vehicle. But if the speed becomes equal to Gra upon h, it has tendency just to topple, and if the speed exceeds this limit, v equal to Gra upon h, if v is greater than Gra upon h, then the vehicle will topple, it will fall down. So in order to have the condition not to topple, the speed must be less than Gra upon h, or at the most it should be equal to under root of Gra upon h. If the speed exceeds the limit given by equation 4, that is if v is greater than under root of Gra upon h, then the vehicle will topple. If the speed is less than or at the most equal to under root of Gra upon h, then there is no danger of toppling. So let us stop here. Thank you.